Edexcel Core Pure First Order Differential Equations, Separation of Variables. So now we're going to look at some linear first order differential equations in a little bit more detail. First we need to look at the terminology. This equation is linear because the only power on the dy by dx in effect is a power 1. There's no square rooted or squaring or cubing of any derivatives. It's a first order differential equation because the highest derivative we have in the problem is a dy by dx, which is a first derivative. The right hand side we've called f of xy, and at the moment that is just some function which is a mixture of the variables x and y, but we need to look at that in a little bit more detail now. So this method that we're going to look at relies on looking at the right hand side, and can we write the right hand side as a product of two separate functions, g of x and h of y. If we can write the right hand side as a product of two such functions, then we can use a method called the separation of variables. So the first thing you've always got to ask yourself is, can we write the right hand side as an appropriate product? So if we look at this first case, I can pull y out of this right hand side as a common factor. In other words, I can write the right hand side as a function of x multiplied by a function of y, and therefore I would be able to separate the variables. If we look at this second problem, it's impossible to pull out common factors or factorize or rewrite the right hand side in a way which would separate the x's as a product of a function of the y's. So this one cannot be done, and we would not be able to separate the variables. Likewise on the third one, even if I used a compound angle formula, which you may have come across, and wrote this as sin x cos y plus cos x sin y, would I be able to separate everything to do with x and multiply by some function of y? No. So in this particular case, by pulling out y as a common factor, the first example would be appropriate for separation of variables. Although this is going to be a recap of a technique you may have met at A level, it will be of increasing importance when we're doing differential equations in further math. So we do need to introduce this again at this stage. So here we've got the differential equation dy by dx is 1 over xy. It's first order because it contains a first derivative, and it's linear because in effect it's dy by dx to the power 1. So it satisfies the conditions of a first order linear differential equation, and what we need to ask ourselves now is, can we separate the x from the y? So if we rewrite this as dy by dx equals 1 over x times 1 over y, then we've got our product of two distinct functions. Now if we multiply through by y, we can get this to y dy by dx is 1 over x, and now if we integrate both sides with respect to x, this could be written as the integral of y dy by dx with respect to x is the integral of 1 over x with respect to x, and this is more simply written as the integral of y dy is the integral of 1 over x dx. So although there's some quite subtle use of implicit calculus here, what you usually do is go straight from that line to that line. This line of working, although true, isn't always necessarily included in our methods. So what we're looking for here is to make sure we can separate the function of x from the function of y as a product, and then it allows us to separate the variables. Usually we can go straight from that step to that step in one stage, and we now have to do the integral on the left hand side with respect to y and the integral on the right hand side with respect to x. So having separated the variables, if we integrate y with respect to y, we get a half y squared. Integrate 1 over x with respect to x is ln mod x, and it's worth noting that you only need one constant of integration. If we had a plus a on one side and a plus b on the other side, then we could just write it as a minus b together and replace it with a letter c. So one constant of integration I would recommend on the right hand side. If we multiply through by 2, we can start to tidy things up a little bit. And if we square rooted, we get y is the square root of 2 ln mod x plus, and I can replace 2c if I wanted to with a new constant called k. So this is our general solution because it contains one arbitrary constant k. So make sure you do the integral on this side with respect to y and the integral on this side with respect to x, and don't forget you only need one arbitrary constant. And when we rearrange this, I've replaced 2c with a different constant k, which isn't essential, but you may find it makes your general solution a little bit neater and easier to work with. So in the general case, once we've got it in the correct form as a product of two functions, here f of x times g of y, we need to divide by the function of y. I'm just going to bracket the dy by dx just to keep things neat and organized, equals the function of x. If we now integrate both sides with respect to x, this could be written as the integral of 1 over g of y dy by dx with respect to x is the integral of f of x with respect to x. Now this integral on the left hand side can be written far more simply as the integral of 1 over g of y dy, and the integral on the right hand side is relatively straightforward. So this subtle use of implicit calculus here, usually we go straight from that line to that line when we separate the variables. It's not essential to put this extra line in, so I'll put a bracket around that. Although it's mathematically correct, you don't necessarily need to put it into your solution. And that's the general premise behind separating variables. If we can get it into that form, then we can apply our integration techniques to get to the general solution. Okay, so you've got to be able to write it as a function of x times a function of y, and it's generally accepted that we can go straight from that form to that form. Just make sure you've got integrating a function of y with respect to y equals the integral of a function of x with respect to x. So in the next session we're going to be looking at applying the separation of variables method.